So today we're going to be talking about big data. So think about, what does that mean to you? Some people have described data as being the new oil, indicating it's a value, has a value that can be extracted from it. This is one way of saying it's a new asset, or a new class of asset, but it's different in some ways. One way it's different is that data can be reused, unlike oil. Another is that its value grows as the volume of data grows. There's a famous quote from Peter Norvig. He's Google's director of research, who said that Google doesn't have better algorithms, they just have more data. Now that might be an overstatement, but one example Norvig cites is translation. Other companies had tried doing translation using data sets that were smaller but more accurate, such as Microsoft used the Canadian Parliament's proceedings, which are in English and in French, since both are official languages. This is a very clean data set, and it's the law, so it has to be translated very precisely. Google instead took a different approach and used translations from all over the web, websites in multiple languages, documents in multiple languages. Some were high quality, some were low quality, but the difference in volume allowed for a much better translation tool. Most people, if asked what big data is, say it's something about along the lines of it's lots of data, or lots and lots of data. In fact, one of the early definitions in 2011 was very similar. Back in 2011, the consulting company McKinsey provided the definition of big data that's shown here. These are bright people and very highly paid, but the definition is bad for multiple reasons. One reason is it says the ability of typical software, or more likely the underlying hardware, changes rapidly. A data manager at a supercomputing center once told me there are no big, old data sets. What was huge a few years back is now large, and what was large is now run-of-the-mill. Think about external hard drives or the USB thumb drives you buy to use with your computer. What would have been huge 5 years ago is now average at best. So, if you look at this definition and take out database software and just say the ability of typical tools to capture, store, and manage and analyze data, when was the first big data problem that occurred in the United States? Think about that for a while you pause this. The answer? 1880. The 1880 census took 7 years to tabulate, which means add up all the numbers. The data was rather stale then, but a bigger problem was looming. The census occurs how often? Every 10 years. At that time, the country's population was expanding rapidly, and it was estimated that the 1990 census would take 13 years to tabulate. Now they have a problem. They would need to start again, with 3 years still left to go on the last census. The government called for proposals, what would now be called a request for proposals, or RFP. The Holworth tabulating machine, developed by Holworth, who had previously been in the Navy, was the winner, and is the machine shown in the photo here. That company later went on to become part of IBM. So if this is a bad definition, how else is big data defined? One of the most widely used definitions is the 3 V's. These were first identified by Doug Laney at Gartner, who was discussing the problems facing web-based companies before the term big data was even coined. Of the 3, most people think of volume, as we mentioned, lots and lots of data, but companies have found that variety, all of the different data formats, the different data sources, both within and outside of an organization, as well as different levels of granularity of data, such as transaction versus product level data, are really the biggest issue. The third V is velocity, which has been described as both how fast data is coming at you, what is known as streaming data, such as the sensors in a self-driving car, as well as how fast executives need to make decisions based on the data. Others have added additional V's. IBM added veracity, the accuracy of the data, and SAP added value, which is sort of obvious in that companies should not be doing things that have no value. It's good to know about the 3 V's in an interview, but as discussed by Thomas Davenport, he's a professor at Harvard and frequent consultant and speaker on the topic, most people really don't like the 3 V's. In this clip, he recounts the story of how big data is like cockroaches.
People talk, as you probably know, about the three V's for big data: volume, variety, and velocity. He said, this is nothing new. Cockroaches have the three V's. They are apparently quite voluminous. One female cockroach can have 150 offspring. There are a lot of varieties, 5,000 different species of cockroaches, and apparently if cockroaches were as big as cheetahs, which is a sobering prospect, they would be able to travel at 50 miles per hour. So I never really liked that 3V thing. I always thought, what if you only have one V? It doesn't, are you kind of out of the running? But I thought it was a neat twist on that classification.
One of the reasons people don't like the 3Vs is that it describes big data based on the problems or issues with it. It'd be like if someone asked my wife to describe me and she said, well, he's old, he's balding, he's not too athletic. I would be like, thanks a lot. So instead of looking at the problems with big data, maybe we should look at what big data is used for. Big data has been described as the fuel of data science. And data scientists they do data science. So what is a data scientist? DJ Patil, who was leading the data science team at LinkedIn at the time, claims that him and Jeff Hammerbach, who was at Facebook, coined the term data scientist in 2008 to describe the people on their teams who are using data and science to create something new. He said they considered the term research scientist, but that seemed too futuristic and abstract. Their teams were focused on data applications with an immediate business impact. 4 characteristics Patil identifies as key to being a data scientist are technical expertise, curiosity, storytelling, the ability to communicate your results, and cleverness. Later, Patil became the first chief data scientist of the U.S. government under President Obama. A little while later, in 2012, in an HBR article by Patil and Thomas Davenport, they identified data scientists as the sexiest job of the 21st century. Now, Harvard Business Review, of course, is not the arbiter of sexiness like People magazine, but only 2 years later, Davenport said data scientists are really data plumbers, because companies had found that data scientists only spent 20% of their time on the sexy part, such as building machine learning models, and spent 80% of their time on data wrangling, finding the data and massaging it into a format that can be used. This is sort of related to the extract, transform, load, or ETL processes often done for data warehouses. One of the first widely used tools to wrangle big data was MapReduce, which we will discuss today. The conclusion you can reach based on this sequence of claims and definitions is that being a plumber is the sexiest job of the 21st century, and big data is the fuel of sexy plumbers. Another way we could look at big data is, what are people doing with it? So it used to be when the internet first started, people used to say, nobody knows you're a dog on the internet, meaning basically you could be anonymous. But as illustrated in this cartoon from Katie Nuggets, it's a website for machine learning. Now, everything about us is tracked on the internet, and companies can know all of our demographics and all of our habits and all of our likes and dislikes. So big data is being used to track all of us. So what started the growth of big data? Why now? Not surprisingly, it can be traced to the growth of the web. In the early 2000s, search companies, such as Google, were trying to index the web. Back then, they did not have a lot of money, so they ran on cheap commodity hardware. But they had to process lots of data, and they had to process it often to keep their index of the web fresh. As it was taking longer and longer, they had a problem similar to what the Census Bureau faced back in the 1880s. To explain the process, let's first take a look at a video by Matt Cutts explaining how a Google search works.
Hi, my name is Matt Cutts. I'm an engineer in the quality group at Google, and I'd like to talk today about what happens when you do a web search. The first thing to understand is that when you do a Google search, you aren't actually searching the web. You're searching Google's index of the web, or at least as much of it as we can find. We do this with software programs called spiders. Spiders start by fetching a few web pages. Then they follow the links on those pages and fetch the pages they point to, and follow all the links on those pages and fetch the pages they link to, and so on, until we've indexed a pretty big chunk of the web. Many billions of pages stored across thousands of machines. Now, suppose I want to know how fast a cheetah can run. I type in my search, say cheetah running speed, and hit return. Our software searches our index to find every page that includes those search terms. In this case, there are hundreds of thousands of possible results. How does Google decide which few documents I really want? By asking questions, more than 200 of them, like, how many times does this page contain your keywords? Do the words appear in the title? In the URL? Directly adjacent? Does the page include synonyms for those words? Is this page from a quality website, or is it low quality, even spammy? What is this page's page rank? That's a formula invented by our founders Larry Page and Sergey Brin that rates a web page's importance by looking at how many outside links point to it and how important those links are. Finally, we combine all those factors together to produce each page's overall score and send you back your search results about half a second after you submit your search.
Although it's not mentioned in that video, processing all of those web pages that Google crawled involves processes that are often called embarrassingly parallel. What could embarrassingly parallel mean? It does not mean that it's shameful. You don't whisper to your siblings, "Don't tell Mom, but I'm doing something embarrassingly parallel." Instead, it means that some process can be broken up and assigned to different people, or in this case, different computers. It's called embarrassingly parallel because if you're a programmer and you tell another programmer you are doing it in parallel, spreading across computers or cores on your computer, other programmers would say, well, duh. In that case, they should be embarrassed if they did not do it in parallel. And possibly their moms might be too. Back then, Google did not often open source their software, but they often wrote papers about it. Back in 2004, they wrote a paper about how they were processing data across multiple computers using a process called MapReduce. The name of the paper was MapReduce, Simplified Data Processing on Large Clusters. Doug Cutting saw that article and realized it solved his problem, which makes sense, since he was working on a different search engine called Nutch. He started a Hadoop project, naming it after his infant son's stuffed elephant toy, and was hired by Yahoo to continue the project. Yahoo saw it as being useful for much more than just building the search index. Yahoo open sourced Hadoop, and it took off. It became the big data platform for a number of years, and many big data tools were designed on top of it, building an entire ecosystem of big data tools. For an interesting and non-technical history of Hadoop and Yahoo's involvement, see the Wired article from back in 2011. The MapReduce example in Google's 2004 paper, the one it's most often used for illustrating these concepts, is called word count. As an example, assume you are Google building an index of the web. One question you may have is, how unique is every term in a user's search query? Using the example from the video with Matt Cutts, possibly cheetah is less common than running, which is possibly less common than speed. If that's the case, then when searching the index, documents with cheetah may be more relevant. This is term frequency, and that's what word count does. It calculates how often each word in a document occurs across all the pages Google harvested. Here we look at an example that's more to human scale. Assume we wanted to count how often each word occurred in Lincoln's Gettysburg Address, which is shown here. If we had a team of 5 students, how could we process this? You could think, well, maybe Scott will do it. We can get coffee at Starbucks and come back when he's done. I wouldn't be looking too agreeable to that. How else could you approach it? The MapReduce approach used in Hadoop is to divide large amounts of data, such as the text from crawling the web, or in our smaller case, Lincoln's Gettysburg Address, into blocks of text and spreading them across many computers to be processed. With a team of 5, we could divide up the text, and each student would count the occurrence of words in their segment of the Gettysburg Address. Since we're just counting word occurrences, we don't even need to break up paragraphs or even sentences. We can just split the text in an equal number of lines for each student. At least initially, each of the students on our team could work independently. If you are counting the first segment, and I'm counting the second segment, the word nation occurs in both, but we can each work independently. At some point later, we will need to bring our lists of words and their counts together. Here we are looking at our first segment from the Gettysburg Address. If we were counting on paper, as we see a word for the first time, we could write it down and then put a tick mark next to it. If a word occurs multiple times, such as nation, we would make another tick mark each time the word occurs in this segment. This would be very simple to do, but the word count example using MapReduce has simplified this even further. We will walk through an example of MapReduce, but first we need to cover two concepts that are key to MapReduce. The first is how Hadoop manages data and spreads out the work to be done in parallel across multiple computers. The second is key-value pairs. The first concept we need to cover is how Hadoop manages data. From the programmer's perspective, Hadoop looks like one big file system. The programmer does not need to know or be concerned with the fact that the data is spread across hundreds or even thousands of computers. Coordinating all of the action is a name node, or a driver node. You can think of a name node as a conductor for an orchestra. The music is made up of all the instruments playing together, but the flute player only has their instrument and their music. The tuba player has their tuba and their music. The conductor is responsible for the coordination. MapReduce is like that. Each node has its chunk of data, and the name node says to process a specific chunk using a program provided by the name node, and then the name node directs where the results go. The name node has a file system that looks like when you put something on your hard drive. When data is added to the system, the name node actually divides up the file and spreads chunks around and creates duplicate chunks on different nodes because, well, on large systems, things break. You cannot update a file, you can only read it or delete it. The second component we need to understand is key-value pairs. MapReduce is composed of two components that a programmer must write code for, a mapper and a reducer. Both of these talk the language of key-value pairs. So what is a key-value pair? This guy in a picture is an expert at processing key-value pairs. He does it all night long. Who is he? The bouncer at a nightclub. What does the bouncer do? He looks at a chunk of data, otherwise known as a driver's license. Here we are looking at the driver's license for Lucille Ball, a famous comedian from years ago who had her own TV show. The bouncer looks for a key-value pair, such as the key, DOB, standing for date of birth, and the value is a specific date. If the date is before a certain date, he waves the customer into the bar. If the value is after a certain date, he turns them away. In a minute, we will see that this looks a lot like the mapper in a MapReduce program. MapReduce consists of three stages: map, shuffle, and reduce, and they occur in that order. Each mapper gets a chunk of data and works on their chunk of data while the other mappers are working in parallel on other chunks of data. During the map stage, the mappers do not need to talk to each other. First, we will do a very simple example of a MapReduce job you might do when pooling your change to go on a family vacation. Assume you and your family have been tossing your change into a jar. The jar is now full, and you could really use the money. To count the change, each family member gets a pile of random coins and sorts them by denomination. One of the mappers, which is you, picks up a coin and says, "This is a dime," and you put it into your dime pile. You map the coin to a key-value pair, with the key being the word dime, and the value being 1, because you're holding one dime. And you put that dime into your pile of dimes. After each family member has finished sorting their pile of coins into the different denominations, each chunk of data, in this case a pile of coins, has been mapped. We now move to the shuffle stage. Assume your mom is the name node or driver node in charge of the whole process. So she assigns each family member a denomination, which is a key in the language of MapReduce. You are assigned the key pennies. In the shuffle stage, each family member passes their pile of pennies to you. Similarly, you shuffle your piles of nickels, dimes, and quarters to other family members assigned those specific keys. Now we start the reduce stage. Here you are counting the pennies, and when you are done, you output a key value pair where the key is the word pennies, and the value is the number of pennies that were in the jar. Now we are going to walk through illustrating word count using the Gettysburg Address we looked at earlier. This illustration is from Yahoo's tutorial on MapReduce and shows the two components a programmer needs to write, the mapper and a reducer. The shuffle process the system performs for them between these two stages in the process. You can think of each square, or what's called a node in this diagram, as a computer. And then the same computers are used in the mapping and reducing stages. When all of the mapping is finished, the shuffle is performed, and then the reducing is done. So at different stages, each computer is first wearing a mapper hat, and then a reducer hat. The code that the programmer needs to write is a part inside of each node, in a sort of pinkish colored box that says mapping process and a reducing process. For each MapReduce job, the programmer writes a single mapper program and a single reducer program. The node doing the coordination, the driver node or the conductor that's not shown in this diagram, is responsible for sending the code to each node that is processing a chunk of data. In the mapping nodes, the white boxes at the top represent the chunks of data coming in. In our example, this would represent those strips of the Gettysburg Address going into each of the mapping processes. In a real MapReduce job, these would be very large text files. The mapping process is very simple for word count, and you are going to write it in Spark during the class exercise. The mapper takes each word in the text it's given and produces a key value pair, but it's extremely simple, way easier than our bouncer's job reading licenses. Instead, for each word, it generates that word as the key and the value 1. Yes, for word count, the value is always 1. In the following slides, we will walk through our Lincoln's Gettysburg Address example. Here we have the second line of the Gettysburg Address going into a mapper as one of the input chunks of text data. Each word of this line would be processed and used to generate a key value pair with the word as the key and 1 as the value. Here we are showing just 2 of those words, nation and dedicated, but each word would be processed the same way. You might be wondering, why the value 1? Well, the number of times the word nation occurs within the word nation is once. I know, that sounds stupid, but it keeps it extremely simple. Think about if you needed to read a textbook and count the number of times each unique word occurred in the book. Keeping all of that in your head would be impossible. However, if each time you encountered a word, you just had to say that word and the value 1, regardless of whether you had already encountered that word, that would be infinitely easier. It would also be extremely boring, but computers don't get bored, at least not yet. We also show node 3 processing another chunk of the text, and one of the key value pairs it generates also has a key nation and a value of 1. In total, there are 5 occurrences of the word nation in the Gettysburg Address across our 5 chunks of data. There are 4 occurrences of the word dedicated and 2 occurrences of the word dedicate. When doing natural language processing, a module known as a stemmer will often be used so that words with the same base, such as dedicated and dedicate, would all be considered the same word. Each key has a node it is assigned to in the reduce stage, so let's take a look at how the shuffle stage gets our key value pairs from the mappers to the correct reducers. Looking back at our MapReduce process, in the shuffle stage, the key value pairs generated by the mappers are each sent to the reducer node that was assigned that key. The shuffle stage is performed by MapReduce without the programmer having to write any code for that process. Since we are looking at 2 words in our example, dedicated, and nation, we will assume that dedicated is the key assigned to node 1 for the reduced stage, and that nation is assigned to node 2 for the reduced stage. The keys are generally assigned in a way that tries to balance the workload. Let's look at the shuffle stage for our example. At this point, the nodes change from wearing their mapper hat to wearing their reducer hat. So the nodes shown in the lower half of the screen for the reducer stage are actually the same 3 nodes that were used in the map stage above. Each key, which in our case is a word, is assigned to one of the reducer nodes. For word count, multiple keys would be assigned to each node. Since we assumed that the word dedicated was assigned to node 1, all instances of that word were processed at any mapper would be sent to node 1. Here we show an instance of the word dedicated being sent from node 2 to node 1 along with the value for that key, which is always 1 in word count. The word nation is one of the keys assigned to node 2, so the key value pairs for the key nation from any mapper are all sent to node 2. One of the key value pairs generated for nation was already at node 2 after the map stage, so it stays there. The key value pair for nation that was mapped at node 3 is also shuffled to node 2. In total, there are 5 instances of the word nation in the Gettysburg Address, 4 occurrences of the word dedicated, plus 2 dedicate instances if we are using a stemmer. The MapReduce shuffles the key value pairs from the nodes where they were mapped to nodes where they were reduced without any additional effort by the programmer. Let's now take a look at the reducer stage. MapReduce handles the shuffle stage to get each key value pair from its mapper to reduce a node that it was assigned to. This eliminates the biggest headache when programmers have tried to build systems that span hundreds of computers. As the key value pairs arrive at the reducer, MapReduce creates a list of the values for each key. We were looking at the keys for the words dedicated and nation. Dedicated occurred 4 times in the Gettysburg Address. Nation occurs 5 times. Dedicated was assigned to node 1, and nation was assigned to node 2, so we have the list shown here. The programmer needs to write code that given a key, such as nation, and a list of values, which in our case is a list of 1s, will then output a new key value pair that's the result. For word count, let's use the key nation as an example. If you wanted to tell someone how many times nation occurred, what would you do with that list? Well, you would add up the 1s in a list. And you learned how to do that in grade school, so that's pretty easy. In the lower left-hand corner of the screen is the code you would need to write for the word count reducer. That's it. Here we have a function named reducer, and it takes 2 inputs. The first input is a word that would be the key. When the second node was processing nation, the word parameter would be the word nation. The value parameter would be the list of 5 1s. The first line of the function creates a new variable named sum and sets it to 0 because, well, we haven't counted anything yet. The next 2 lines are the meat of this function. For each of the values in a list, which are each a 1, it adds that value to the existing sum. After all 5 values have been processed, the variable sum will be equal to 5. The last line of the function is the output, which is the key, which is the word nation, and the value 5. As we have seen with word count, MapReduce allows programmers to process large volumes of data in parallel across hundreds of computers without every programmer needing to address the headaches of coordinating all of those computers. Next, we'll try a hands-on exercise where you will program word count using Spark, a modern successor to MapReduce, to analyze Yelp data to see what words do people use the most when discussing restaurants on Yelp.